Okay, so welcome back for this fourth lecture on mean-field games. So what I'm going to do today is to discuss about things that I have not discussed so far, but which are included in the slides. And so the first thing that I would like to discuss is really the convergence problem. This is something that is absolutely necessary to discuss. But what I called, not what I did 2 days ago by using the notion of approximate Nash equilibria. But here, what I want to do is to discuss what I called on the same lecture on Tuesday, the North Face. And so this is what I want to discuss. So in fact, this is the second part of the lectures that of the slides that I gave you yesterday. So you can find this in the slides. This is the second section. But since it took me a long time to get the results on the master equation, I didn't have time yesterday to discuss about the convergence problem. And this is something that is absolutely necessary to discuss in a course on mean-field games. So this is lecture 4. Oh, let me share my screen. Okay, so you see the screen. And so this is lecture number 4. And the first thing I would like to discuss today is really what we call the convergence problem. And so I insist on the fact that this is another way to make the connection with the game with finitely many players. So this is again a way to make the connection with the game with finitely many players. And so what I told you about this on Tuesday was that there was a quite simple way to make the connection between the MFG and the original game. And this way of doing was to use the solution or a solution of the mean-field game and to use the equilibrium feedback of the solution that you have constructed to insert this into the game with finitely many agents. So you have to recall this. So recall a way to make the connection. A way to make the connection is to solve the MFG, then to get an equilibrium feedback, and to insert this equilibrium feedback into the game with capital M agents. Well, that's something that is, from the practical point of view, I explained on Tuesday. So once again, see lecture number 2. I explained you on Tuesday that this was absolutely justified to do so from the practical point of view, and that even more, this is a way to obtain what we call decentralized approximate equilibria, in the sense that to implement the resulting strategy, once you have computed the equilibrium feedback, in fact, you just need to plug or to insert your own state. So this is something that is absolutely useful from the practical point of view. Anyway, from the mathematical point of view, this does not completely answer all the questions that you could have in mind. And you could say, well, now I am going to do the converse. I am going to solve for the min-field game, for the game with finitely many players, and I'm going to let the number capital N of particles tend to infinity. And I want to see whether if I do so, I am able to get a solution of the min-field game. So that's the question. So here, this is another point of view. And so what we are going to do is to say that we solve for the game with capital N players. We let N tend to infinity. And the question is, do we get asymptotically a solution to the original min-field game or to the min-field game? So do we get in the limit a solution to the min-field game? Okay, so this is usually, if you read a bit of literature on min-field games, so this is exactly what people call the convergence problem. This is really this one that is called the convergence problem. So this is another way to make the connection. And this is a really natural equation. But as I told you on Tuesday, this is certainly more difficult. And the reason why this is more difficult is that when you go back to the n-particle system and you try to solve this, this is possible to find equilibria, at least from a theoretical point of view. But then you have questions of compactness. And so if you try to use compactness on the feedback functions, then this is almost impossible because the dimension is going to increase, and it seems pretty difficult to get some strong compactness arguments as the dimension increases. So there are two approaches for solving this equation. The first one is what I'm going to tell you today, which is using the master equation. So you directly benefit of the fact that everything is nice in the limit. So I'm going to cheat in the sense that I'm going to postulate that, or to assume that the Lasry-Lyon's monotonicity condition is in force, and that my coefficients f and g are smooth N-off. And as a result, if you remember what we did yesterday, I know that there is a classical solution to the master equation. I know that I was a bit quick at the end to explain to you what was exactly the details of the proof, but I explained to you that this was really a equation in the field. And so once you have solved the master equation, you should say, well, what is the interest for having this equation? Well, I'm going to show you today one possible interest. The very good point when you use the master equation for solving the convergence problem is that it gives you a rate of convergence. So you really have something that is sharp. So this is one first approach. So first approach. So use the master equation. So this is just, let's say, under the Lasry-Lyon's condition, because I need a classical solution to the to the master equation. So basically, I should say that this is the typical setting where we know that there is a classical solution, because this implies plus smooth coefficients, I should say, plus smooth coefficients. And we know that this implies existence of a classical solution to the master equation. So this is what I'm going to explain to you today. And the very good part of this approach is that at the end of the day, you get rid of convergence. And even more, you can push further. You can get some central limit theorems, so some large deviation principles for the empirical measure of the system. So this is something that is really, really robust, but this is demanding in terms of the assumption, because once again, you need this classical solution to exist. As for the references on this approach, so this is in fact the real purpose of the book with Cardaliaguet, so myself, Lasry and Lyons. This was really the purpose of the book, to explain this method. Now, this is not the only method that exists. And as I told you before, you have another one, which is based on compactness arguments. When I say compactness, you have to think of compactness on the equilibrium strategies or the equilibrium controls of the game with n players. So this is really compactness on the controls or the equilibrium controls of the capital N player game. The point is that if you want to have, as I told you, if you want to use strong topology, let's say if you have feedback functions and then you want to use strong topologies, then this is too much demanding, because you need capacity on your functions. And as I told you, you are missing a lot of a priori estimates as the size or as the dimension is increasing. And at the end of the day, you're not able to make the proof. And I don't think that there is any proof using a very strong compactness topology or strong topology for the compactness argument. So instead, the approach that has been developed was to use the notion of relaxed control. And I know that some of you know this theory. So relaxed controls. In fact, relaxed controls, you could regard this, or you should regard this as a compactification of standard controls. And the way you compactify is that somehow you replace your controls by measures. So this is a kind of randomization of the controls somehow. For those of you who come from analysis, this is what you should call Hume's measure. And so when you do this relaxation of the control, then it turns out that this is much easier to get some compactness argument, because having capacity on probability measures or finite measures is quite easy if the state space is compact. So this is an approach that has been developed by Daniel Laker, and he did a wonderful job on this. And I think that I mentioned these works a few days ago. This was on Tuesday, but once again, I emphasize and I advertise the existence of these works. And really, really what he did is really nice. So at the end of the day, this is less demanding in terms of assumptions. So which is a really good point, because you don't need as many assumptions than in the first approach. But you could say that the drawback is that since this is a compactness method, there is no rate of convergence. So this is as usual. There are some advantages on one side or on the one hand, and some drawbacks on the other one. Anyway, all these approaches are complementary. So you could say that there is no right. Well, so today I'm going to speak about the first one. So the first approach using the master equation. So this is exactly in line with what we discussed yesterday. And really, the starting point is to go back to the Nash system. So the Nash system is something that I have not spoken about, and this is one of the things that I should speak about to have a kind of complete overview on min-field games. And what I'm going to show you is that this Nash system, which is somehow the analog of the HAB equation, but for a game with finitely many players, this Nash system somehow is or becomes in the limit the master equation. So this is something that is really nice, and you really see how the master equation appears when you start from the game with finitely many agents. So let me write this properly. So this is paragraph number 1. From the Nash system to the master equation. So what is the setting for this Nash system? Well, this is exactly the same as the one that we have been using for 4 days. So but now you have capital N players, and the dynamics of any of them, or let's say of player number I, is of this type. So we know, or you remember certainly, that the BIs are independent Brownian motions. So I don't think that this is necessary for me to repeat this. And then you have the cost functional, and these are things that we defined on Monday. So this is pretty easy for me today, because I have all the necessary material to speak about this. And I know that the cost to player I is G of XTI. And then I have this empirical measure, and I feel quite necessary to emphasize this in blue. And then I have the running cost. I'm sorry. And this is F XTI. And then I have mu bar N T here plus 1/2 Ti squared, the kinetic energy. Well, so really, 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 you have to remember that this was, or this is, the empirical measure. If you don't remember this, there is no chance for you to understand what we are going to do. Okay. And now the question is, we want to find a Nash equilibrium for this system. And in fact, I gave you the definition of a Nash, but I have not really told you how to find this from the practical, or how to formulate mathematically, I should say, the search for a Nash. So how to look, or how to find a Nash equilibrium. So here there is a subtlety, because in fact, when I say a Nash, I should specify whether the equilibrium is constructed upon controls in open or closed loop form. What I'm going to do here is to restrict myself to Markov strategies, which is something that is pretty natural for the application. So it really means that when you decide of the feedback of the strategy that you want to implement, it means that you require alpha ti to be of the shape. So this is your process, and you want your process to be, so this is the process here, and you require it to be of the shape T, xt1, xtm. And now here, this is a function. So you could complain that I am using the same notation for both, despite the fact that they are not the same. But here there is time in index, and here I put time in parentheses. And this is just a way for you to see that one is a function and the other one is a process. And so this is really, this is what you do in practice. You implement your strategy, let's say, in terms of the position of the system. And so then you want to find a PDE characterization of Markov equilibria. So once you have decided to restrict yourself to Markov processes or to Markov strategies and thus to Markov processes, you get a PDE. And this is something that is pretty classical in probability theory. Once you have a Markov structure, you get a kind of PDE. So associate with the game a PDE. And so the way you do this is to say that you freeze the feedback functions of n-1 players, and then you compute what is the best reply or what is the best response of the remaining player. So to find this PDE, in fact, it's going to be a system of PDEs. So you freeze alpha 1, alpha I-1, alpha I+1, alpha n. So these are the feedback functions for the strategies played by players. So 1, 2, I-1, I+1, capital M. And then you want to compute the best response of player I itself. So here, this is player I, and here you have all the others, all the other players. Okay. So how to do this? Well, you say, I'm going to compute the best response by computing the value function. Okay. And then plus the optimal feedback, exactly as we did before, by solving a HAB equation. So what should be the HAB equation? So let me write this properly. I know the dynamics of all the players except player I, and player I wants to minimize this cost functional, keeping in mind that all the other strategies have been fixed. And so I know that I will get a PDE for this. And so the PD is going to be, so the HAB equation that you get is dTui. You have to pay attention that the value function here, when I say value function, this is a function that depends on all the states in the system. So X1 is somehow the initial state of player one, X2 is the initial state of player two, and so on. So here, this is an element of RD to the N. Okay, and to simplify the notations, I'm going to denote this by X underline. So really my PD will be a PD depending on T and X bar. And so I would have the time derivative. Then I notice that all the players are driven by independent Brownian motions. So I should get 1/2 the sum of Laplace operators acting in the coordinate xj on UTX bar. And then I understand that there is a drift, so I have to account for the drift. So here I should pay attention because there is the drift for the players which are not equal to I. And then I know that those people are choosing alpha j TX bar. Okay. And this is acting on the derivative. So here, this is an inner product in RD, UI TX bar. But I also have, for sure, I also have the case when I need to specify what is the optimal feedback or what is the strategy of player I itself. And I know that in this HAB model, the optimal feedback, or maybe I should say, let me put this as a Hamiltonian. So let me say that this is the infimum. I will get the infimum over beta in RD of beta inner product dxi uti tx underline plus 1/2 beta square. So this is my kinetic energy. And then I have the running cost F xi mu x underline n. So this is a shorthand notation for the uniform measure on x1 xn, and this is equal to 0. I don't think that I have forgotten something, so this seems to be okay. And then what is the boundary condition? The boundary condition is what I'm paying at the terminal time. And I know that this is G of xi mu bar n x underline. So that's the equation. For sure, if you go back to the Hamiltonian that you have here to this term, you can simplify. This is exactly what we did on the first lecture for getting the HAB equation in the MFG formulation. And I know that it's going to be minus, so the best beta, the beta star, if you want, the optimal one is minus dxi UTITX underline. So I get exactly at the end of the day, minus dxi UITX underline, acting on itself. Okay, plus 1/2 the same thing. You could say that I could simplify, but this is absolutely, there is a question. If you have any question, please. Okay, so this is the two terms that I have. And so now what to do with this? Now you have to implement the fact that you have an equilibrium if the best response is the equilibrium itself. So then you say that you implement the Nash condition. And so you have that a tuple of strategies, of Markov strategies, is an equilibrium if the best response matches the equilibrium itself. So here, what is the best response? The best response is the optimal feedback. And so the optimal feedback is here. This is this minus, or this one here. This is my optimal feedback. And so at the end of the day, what I get is that to get an equilibrium, I must have that alpha I t x underline has to be equal to minus dxi ui t x underline. And what I'm going to do is to come back, but I should have this. This should be for any I. This should be for any I. So what I'm going to do is to highlight this. And now I'm going to plug these identities into this system. And this is the way I get what we call the Nash system. So finally, the conclusion of the analysis is that I get as a Nash system, so dt ui tx underline plus 1/2 the sum over the j's from 1 to n of dxj ui tx underline. And now the very good point is that I can simplify, or I know exactly what happens in the first order terms. And I would get, so sorry about this. So minus the sum from j equal 1 to j equal n of dxjuj. So this is exactly, now I know that this is my feedback, acting on dxjui, if I am correct, yes. And then plus f xi mu bar n x underline plus 1/2 dxi ui tx underline squared, and this is equal to 0. And you have the boundary condition tx underline is gxi mu bar n x underline. Well, this is really what you have to call the Nash system here. I'm sorry for those of you who know this already, but this is absolutely necessary to get this system in order to understand what I'm going to do. Okay. Okay. Now, well, some question. You could say, can we solve this PDE system? So yes, the very first thing I would like to say is that this is a PDE system, So you have capital N equations. Why capital N? Because you know that the indices I that you have in the equation is running from 1 to n. So you have capital N equations. And each equation is in dimension n times d. So now I guess that you really understand what is the difficulty, the numerical difficulty to solve these kind of things. It could be a mess to put this in the machine. And so this is one of the reasons why maybe taking the limit is indeed a very good point to reduce the complexity. Now, what about the existence of classical solutions to this PDE system? Well, there is something that is really nice in this system. This is the fact that, in fact, this is non-degenerate because you have the sum of all these. I'm sorry, here there is a mistake, by the way. This is the Laplace. This is the Laplace. Was it okay? Yeah, this was okay. So you have the sum of all these second order derivatives or second order Laplace terms. And because of this, the PDE system is non-degenerate. It makes a very, very subtle difference with respect to what I had yesterday for the master equation. Somehow, this system is non-degenerate, but it becomes degenerate in the limits. And this is something that should be clear for you somehow, because what is the limit? Well, the limit is the limiting solution gives me the measure of the population. And the measure is completely deterministic. Precisely, you removed the noise by averaging over the whole population. So in the limit, there is no longer a noise that is spread out along the whole system. Each player has its own noise, but this is not the same kind of global noise as the one you have in red in this Nash system. So this is non-degenerate, but if you have a look at the way this is non-degenerate, this is absolutely not uniform in N. And this is one of the drawback or one of the difficulty from the mathematical point of view. Anyway, the fact that this is non-degenerate, I'm sure that you know these kind of things in PDE theory. This is really helpful to get classical solution. This is not completely easy because you pay for this term, and some people in the audience are specialists of this kind of equations. You have this quadratic term here, quadraticity, and because of this, it makes the analysis a bit subtle, and specifically for systems with quadratic terms in the gradients. Well, this is not completely subtle. And in fact, you have a series of papers on these kind of things by Bensoussan and Fraise. I think there is maybe the very first one is in the 80s, and then there is a long series of paper. I don't remember exactly, but this is over 10 or 15 years. So let me just say that these are around the 80s. But for sure, you can find all the needed references in the book with Carmona. So if you go with to my book with René Carmona, you will find all the papers by Bensoussan and Fraise on this equation. But what did these two authors is mostly for elliptic systems. Here, this is parabolic. And so in the book with René, we explained a little bit, or we spend some time, in fact, to explain how to adapt the arguments of Bensoussan and Fraise to the parabolic case. So you can also have a look. This is the book with René. So this is the volume number 2, and this is chapter 6. So when I say classical solution, for sure, you need some assumptions on G and F, but this is as usual. I'm not going to complexify things. So F and G are bounded, smooth bounded derivatives, including in the direction of the measure. So I don't want to make it too difficult here. I just want to give you the basic philosophy. If you want to get the details, please go to the references, or you can ask any question if you want. Okay, so there is a classical solution, and once you know that this is classical, basically this is unique. Okay, the fact that this is unique tells you that there should be a lot of symmetry in the system, because if you have a look at the equation, when you freeze the label I in the PDE system, so exactly as I did, so let me erase this. So if you freeze really this index I, you see that in fact this is completely symmetric in the remaining variables. And it says that if you take UITX underline, and if you make a permutation of the older variables, not xi, but the other ones, then it's going to solve the same equation. And so at the end of the day, by uniqueness, you should get that the solution after permutation should be the same as the original one. And so the solution keep track. So it retains, the solution retains the symmetry of the model. If you remember my lecture on Monday, this was part of the things that I claimed just intuitively or as a kind of heuristics, but in fact, you can make them really, really rigorous. And so when I say that, it means that if you have a look at UTX, X underline, so this is a function, let's say, a function UTXI, and then the orders. So the orders, this is xj for j different from I, and this is symmetric in these arguments. And even more, what you can notice is that, in fact, since F and G here are the same, whatever the particle I or whatever the number of the particle, in fact, this function U here, this guy does not depend on I. Oops, sorry. So this is something that is absolutely rigorous. By uniqueness, you get this. You get that UITX underline. This is really, I insist that this is something that is, this is a result. Let me write this in black so that this is clear for all of you. And once again, this is symmetric, where U is again a function RD times n-1 with values in R. Well, you could say, well, so that's almost my result. Okay, no, not that much. The first thing is that, okay, I removed the index I here, so there is no longer an I, but implicitly, there is an M. So I'm not going to put this, but pay attention that this depends on capital N. So this guy, this depends on capital M. So this is not so easy because you still have capital N in the story, and precisely you want to let N tend to infinity. Anyway, maybe let me put N just to be clear that there is N in the story. Anyway, so when you have something that is symmetric, somehow a function of a symmetric function of the arguments is a function of the uniform measure of these arguments. So it means that this guy, I could reformulate this as, let's say, let me write this as UN of TXI, and then the empirical measures of the orders. Because when you have a symmetric function, well, the only thing you need to know is where are the points in total. You don't need to know who is who. You just need to know where is the global population. And so this is encoded in the shape or in the form of the empirical measure or the uniform measure. Or equivalently, I could say that this is a function of UTNXI and the whole uniform measure on all the particles, because I can play for free with the fact that XI is given first. So this is pretty easy to change the definition of XI so that I include the mass of xi in the right-hand side in the last argument. So if I do so, this is just to show you that what I'm doing right now is to try to recover something that is really, really similar to what we did yesterday for the master equation. But you have to understand that at this stage, this is just a probability measure, or this is a probability measure, but only of the type or of the uniform type yes, I would say on the uniform type. So just to emphasize what I'm saying here is that this argument for conveniency, I'm writing this as a measure, but I'm not claiming that UN can be extended easily to the whole space of measures. What I'm doing here is that I'm writing the symmetric dependence as a dependence on the empirical measure of the system, or the uniform measure on the points, but I'm not claiming that UN can be easily extended to the whole space of probability measures. So this is just a convenient notation, but in no way I have told you that UN could be extended to the entire space of probability measures. For sure, I could extend in a completely arbitrary fashion, but this would be useless because certainly this would be non-continuous, and so this wouldn't be non-interesting. So what would be really difficult would be to prove that UN extends in a continuous manner to the whole space of probability measure, and that this continuity manner would be uniform in N. So this is something that I do not know. Okay. So this is where we are. So now we want to recover. So I don't remember what was my first one. Oh, so no, this is still part of the first one. So the first one is pretty long. Sorry about this. So now we want to prove that once we have postulated this, it should be possible to recover the shape of the master equation. So now what is the ansatz? Well, this is the same ansatz as the one we had on Monday. If you remember well, what I told you on Monday was that certainly this was pretty reasonable to say that, in fact, asymptotically, it was possible to remove the N in green here. So saying that UN could be approximated by a function that is defined on the space of probability measures. So the ansatz is to say that there exists a function. I'm going to put a bar just to distinguish from the solution to the master equation that I had yesterday. So there exists a U bar defined on the whole space. So here I put P2 because this was the setting that we had yesterday, and I'm going to use that next, such that in fact, U, so UTX underline, is approximately equal to U bar TX. So this is I here, XI, and this is mu M X underline. So really, this is the program that we had on Monday, but now I'm going to make it rigorous. But first, this is just an ansatz. Okay, let me do this. And now take this just to explain to you as an equality, right? I said this is equal. This is not true, but this is just to understand how things are going on in this story. And what I'm going to do is plug the equality in the Nash system. Right? And see what it gives for U bar. So what does it give? Or what does it say for U bar? So this is my equation. So let me take the terms in this equation and let me show you and let me explain to you what I do obtain at the end of the day when I replace formally UITX underlined by this U bar on the space of measures. So I take DTUITX underline. Well, if I take the equality for being granted, then I should have DTU bar TXI, or maybe if you prefer, I say approximately equal anyway. This is just intuitively. I get the term derivative, so this one is pretty easy. Now let me take the third term. So this one. So maybe I'm going to call this A, B, C, and then there will be D. So let me explain to you C. So this was A, and now let me do C. In C, what I have is the sum J from 1 to capital N of dxj u j tx underline inner product dxj u I tx underline. And so now I say, well, this is approximately equal to, and now I have to be really, really careful. So I will have dxj u bar txj mu bar and x underline. Inner product dxj u bar txi mu underline x. So the empirical measure. And now I have to compute those derivatives. How to compute this? Well, if you remember well, these are computations that we did yesterday. This is exactly the dictionary that I mentioned yesterday to pass from the derivative on the space of probability measure to the Euclidean derivatives. So here what you have is that you have, when you take the derivative here, there will be the standard derivative of u bar in x, so dx u bar txj mu x underline n. And then I need also to take the derivative in the measure argument. And I know if you remember, or you know if you remember what we did yesterday, is that we get 1 over n d mu u underline txj mu bar n x underline xj. So you really, really, really use the computation on the space of probability measure. And then this is inner product. And you have to play the same game for the last one. And so you see that this derivative is acting on this if I is equal to j. So if I is equal to j, you have delta ij for the Kronecker symbol, dxu bar txi mu bar n x underline. And once again, you have this 1 over n d mu u bar tx. Now this is xi mu bar nx underline xj. So the notation are a bit awful, but well, no choice. Okay, so now let me expand this. So the term now is equal to, so I will get minus the sum from 1 to capital N. So what do I have? The first thing that I have is that, so let me remove the sum. Sorry about this. The first thing is that I have this term acting on this one. But this is only if I is equal to j. So at the end of the day, I just have dxiut xi, because I has to be equal to j. And so this is squared. Now I have this one acting on this one. Then I have all the j's. And so I have minus 1 over n, the sum over the j's from 1 to n of dxu txj mu bar nx underline inner product d mu u bar txi mu bar nx underline xj. Good points. Now what about the other ones? So let me remove all these arrows. Okay. Now I have this one here that is acting on this one. But there is only one guy in this story because I is required to be equal to j. So at the end of the day, I am left with capital O of 1 over n. And it remains to see the very last one. But this is the same. I will get 1 over n, 1 over n here, and 1 over n, and I make the sum. So it's going to be n over n squared. So this will be 1 over n at the end of the day. So the only thing that I have, in fact, at the end is this 1 over n. So for sure, I'm going to forget for this 1 over n. Now, you have to realize that this is really, really, really close to what we had yesterday in the master equation, because the first one, for sure, I'm not going to change it, but the second one is an integral. What I'm going to say is that this sum normalized by n, this is the integral with respect to the uniform measure of a suitable function, and this is this one. So I take the integral RD of dxu underline, so this is the first one, t, and then I have this variable xj, I say this is v, then I have mu bar nx underline, d mu u bar txi, mu bar nx underline, and then this is v, and this is d mu bar nx underline v, plus capital O of 1 over n. And now if you don't believe me, you come back to the lecture that we had yesterday, and you will compare this term with the terms, one of the terms that we had in the master equation. So let me do this. So I think this was the lecture that we had. So this was the equation. And then you recognize exactly this term. This is the one. This is our guy. So when we do this approximation, then we managed to recover some of the terms of the master equation, and you are going to see that, in fact, at the end of the day, we have all of them up to this remaining term, 1 over n. So this was for C. Now let me do B, which is a little bit more demanding, and then D will be absolutely easy. So B, as for B, so B, I have to be really careful. So this is 1/2 the sum of the deltas xj with j between 1 and n of u I tx underline. And so what I say is that this is approximately equal to 1/2 the j's dxj. So there is a trace here, trace of this dxj of u t xi mu bar and x underline. Okay. And I play the same game. I play the same game as the one I did just a few minutes ago. So this is delta ij dx. So there is a bar on u, should not miss this. Dx u bar txi mu underline x bar plus 1 over n d mu u bar txi mu bar and x underline xj. Good. And then this guy is dxj. So there is a new derivative. Okay, there is a new derivative. Well, I have to do that. So what do I get? So it gives me, so I will have delta ij, and then if I is equal to j, I take a new derivative in the first variable, and I have d2x u bar txi mu bar and x underline. Plus, then I have delta ij. This is if you're lost. So this is this one acting on the, on this one here. But what I know is that when I take the Wasserstein derivative, I have 1 over n. So here I'm going to say that this is O of 1 over n. And since there is only one guy in the sum because of the Kronecker symbol, it's going to be put in the remainder. Now I have this derivative acting on this term. But again, this is only if I is equal to j, and then I get 1 over n. So I can forget for this one. And so the very last one is xj acting on this term. No, I'm sorry, I forgot one. There is xj acting on this one. So here you need to take a new derivative in the measure argument. So each time you have a derivative in the measure argument, you get a new 1 over n. So in fact, you get plus O of 1 over n squared. Okay. And last point is, oops, no, not at all. And so the very last one is this one here. And now you have to take the derivative of this one. And yesterday, this is what I called dv. So there is 1 over n dv d mu u underline txi mu bar and x underline v. Very good. So where are we at the end of the day? We said that this is equal to, so the first term here, so when you make the sum over the Kronecker symbol, you just have 1/2 the Laplace. And then you will have the sum over the j's I'm sorry, I did a mistake here. This is not V, this is xj. Sorry about this. This is xj. So then I have to take the trace of this guy, and I make the sum over the j's, and so I get a new integral. But let me write this slowly. So the sum over the j's of the trace of dv d mu u bar txi mu bar nx underline xj. And then for the remainders, this is O of 1 over n. And this is exactly as before. I have 1/2 delta x here, txi mu bar nx underline, plus the integral over Rd of the trace dv d mu u underline txi mu bar nx underline, oops, v d mu nx v plus O of 1 over n. And now I do the same thing as the one I did for the term C. I compared this with what I have in the master equation that we wrote down yesterday, and then you realize that it should be the same. This is exactly what we had. Yeah. So here, now what we have just obtained, this is this one and this one. Okay, and it's pretty easy to see that D will be this one and this one, up to the minus 1/2, but this will be plus 1/2. But if you remember, for B, we had -1, and at the end of the day, this will be minus 1/2. So we recover exactly 1 over n, the Nash system up to this 1 over n remainder. Okay, let me go back to this. And so for D, so D is absolutely trivial. D is approximately equal to, so let me just write this. I don't want to spend too much time on this. This is absolutely trivial. These are things that we have already computed. Txi mu bar nx underline squared. Okay, so you say, well, this is almost the Nash system. This is almost the master equation. So this is the first one. This was my first claim. You can start from the Nash system and then you can recover the master equation. Now there is a big problem in this argument, which is that there is absolutely no way to justify this. You cannot make this a statement. So this is paragraph number 2. From the master equation to the Nash system. So now I'm doing the converse because, in fact, I'm not able to have this approximation, the one I've just pointed out. So what I'm going to do is to do the converse. Instead of claiming that ui tx on the line looks like some function u bar that, in fact, I don't know how to construct directly, I'm going to do the converse. So really, I assume that we have, as I did yesterday, Lasry and Lyons and smooth coefficients. So Lasry-Lyons monotonicity. And then we know that there is U classical solution to the master equation. And now what is the point? Well, the point is to say, I'm going to compare the master equation with the Nash system by projecting U onto the finite dimensional space. So you let U bar I T X underline is U T X I 1 over N, or maybe directly easier, mu bar N X underline. So really, you have to, if the computations are too difficult, which certainly I would understand, you have to understand that here we do the converse. We start from the end, we start from the limit guy, and we use the limit guy and we project the limit guy here onto the space RD to the n. So this is a projection on RD to the n. And now you have this statement. And this is the basis of the argument in the book with Cardaliaguet, Lasry and P.L, which is that you can exactly do all this computation, but now instead of having U bar, you replace U bar by U. So now you put U inside in all the computations that I had. And then I'm going to get at the end of the day that U underline is almost a solution of the Nash system. So statement is that this is, I need U to be smooth. It's really, the fact that this is a classical solution, this is absolutely needed. So I really need this. And now this is my claim. This is almost a solution of the Nash system. What do I mean by almost a solution? I mean that if you take the Nash system that we had here, so let me copy this. Okay. Then let me remove this and this. Right. Then in fact, if you put a bar, so I put a bar here, here. Oh no, this was not the right equation. I did a mistake. So here there is a mistake. I'm sorry about this. So let me remove that. Okay. So this is minus dxj ujtx underline and plus 1/2 dxi uitx underline squared. So this was the Nash system. And now what we are doing is that we put a bar on this. So we put a bar here, here. Okay, and so this is not a solution of the equation. Oh, for sure, this is not, but this is almost a solution. So there is plus a term R, depending on I, Tx underline, such that this is equal to 0. And this guy is capital O of 1 over n. And the boundary condition is the same. The boundary condition is the same. So this is G of xi mu n bar. So there was a bar x underline. Okay, so this is really the starting point. You start from the master equation and then you observe that this is almost a solution to the Nash system. Now the question is how to use that. how to insert this fact in the analysis. So this is not the end. That's not the end of the proof. I mean, now you have to really prove to compare things properly. Here, this is just an observation, but this is a statement. This is no longer intuition. This is really a statement. So 3 is now you have to really compare the feedback and the cost between the game and the mean field game. So now you have to make the comparison. So if you remember the way I spoke about this on Monday, I told you that certainly from a probabilistic point of view, a good point was to follow the evolution of the cost along the dynamics. And here I'm going to do the same. So if I go back to the probabilistic formulation, I should certainly be tempted to follow the dynamics of the cost for the n-player game at equilibrium along the particles. So follow the equilibrium cost. So what does it mean? It means that we know that the particles at equilibrium, they are driven by this, so x underline t, so this is the whole system, dt plus dBti. So this guy here, this is really, I'm sorry, I'm missing an I. There is an I here, so this is I, sorry about this. So here, this is really the feedback. So this is the equilibrium feedback with the minus. I'm sorry, there should be the minus inside. Equilibrium feedback as given by the Nash. Okay, and then when I say follow the cost, it means that I'm going to let YTI that is given by UITX underline. So this is the cost to player number I. And I could be tempted to follow the arguments that we used on Monday, or maybe Tuesday, I don't remember, and to expand, this was Tuesday, to expand this, this cost by means of Ito's formula. And so you compute dyTi. And to compute this, you use the Nash system. Okay, so you use the PD. I'm not going to make the computation. This is Ito's formula plus the Nash system. And at the end of the day, believe me that you will get F XTI, the empirical measure of the system, plus 1/2 dxiuitx underline t squared dt plus, so now this is a bit painful because I have all the possible derivatives, uitx underline t dbtj. So this is what I have for the evolution of the cost. And since some of you know very well backward equations, so let me call this zijt. And I do observe that this guy is ziit. And this guy as well, this is without the minus ziit. So I imitate the notation I have for a backward equation. Okay, that's one thing. Now I'm going to do the same for the projection. So I'm going to compute or to follow the mean field gain value along the equilibrium state of the n-player system. So I follow the n-player system, but along this n-player system, I'm going to compute the value of the MFG. And so now you do the same. Do the same for the MFG value. And so you let YT bar I, that is U bar I TX underline. So this guy is really computed by means of the master equation. So this is really the value of the bit field game. And I remember that somehow I want to prove that the equilibrium value of the game with n agents is close to the equilibrium value of the bit field game. So it makes sense to do this. And you expand in a similar manner. You expand in a similar manner. And now you use the approximate Nash. Approximate Nash. So if you do this, then you get f xit mu bar nt, and you have exactly the same, except that there are some subtleties. So now this is dxi u bar I tx underline t, because you use the same PD structure, but you are paying for the remainder. So you have the, so let me put plus here. So I have to pay for the fact that this is not exactly the Nash system that I'm solving. Where is it? So I am paying for this term here in red. Okay. So I must see that in the expansion of the cost. So this is plus RITX underline T. dt. Okay. Okay. Keep some space. And as before, I have, I'm sorry. As before, I have the sum over the j's from 1 to n of dxj u bar I t x t underline inner product dbtj, sorry. And I call this z bar ijt. Okay, it looks to be correct because you say I'm just paying for the remainder in the approximated Nash system, but in fact this is false. If you really do the computation properly, you have to pay for the nonlinearity. So here there are some nonlinear terms, and you have to pay for this guy. And this guy says that if you really want to see the Nash system, you should expand according to the equilibrium trajectory of the MFG and not the equilibrium trajectory of the game. And so because of this, you pay for something else in the expansion. So precisely what you have is that you have another term in the computation. So this is minus the derivative. So this is Bayeto's formula that you get all these terms. So it's going to be dxj ui bar txt underline inner product. And so here I should pay attention to what I have here. So I should have dxj ui. Is it correct, this one? Yes, this is correct. Tx underline t minus or minus here dxj u underline txt underline t dt. So really it comes from the fact that this is a nonlinear equation that you expand. So this one is okay. And you must see somewhere the fact that in xi, this is the solution of the original Nash system that you use, and that here you expand with respect to the approximated solution. And so for sure, you see that in the remainder, but you also see that in the drift. And so you see that exactly when you compare the original one that is here with the new one that is here. Okay. Okay, so now what is the next point in the analysis? So since I'm happy that many of you know backward equations, because now there is a bit of backward equation. So this is, with my notation, this is z bar I t. This guy is z bar jjt. What else? And this is okay. Yes, maybe here this is zijt, and here this is z bar ijt. Anyway, now what you do is that you compare this guy with this one. So you make the difference. And you want to use a stability argument for backward equation. So let me write this. I'm almost done in my explanation. So dyti minus yt bar I. And so I'm going to compare terms with themselves. So, I mean, I'm going to compare terms one by one. So this one cancel with this one. So this is absolutely easy. Then I'm going to compare this one here with this one, right? So I will have minus z, so there is 1/2, ziit squared minus 1/2 z bar iit squared. Okay. Then I have, let me remove this. I have the remainder. So this one here. So this is 1/n, very easy. Okay. Then what next? In fact, I have the big sum over the j's. So this one could be a little bit worrying. So the very good point is that in this sum, so in this big term here, so I have plenty of terms. I have plenty. So I certainly did a mistake because this is, I'm sorry, here there is no j. This is I. So I did a mistake. This is I because this is the derivative of u bar I. So sorry about this. This is a mistake. So there is an I here. I'm really sorry. And so I did a mistake next. So this was j instead of I. So I exchanged. So here there are 3 mistakes. J, J. And the same here, this is J. Sorry about that. Okay, so once again, and this is the way I noticed that there was a mistake. If you have a look at this, this is a derivative with respect to xj. And as I told you before, this is 1/n, except if I is equal to j. If I is equal to j, this is of order 1. If I is not equal to j, this is of size 1/n. And so what you have is that you have a term that has the shape plus 1/n, the sum over the j's. So maybe I should say capital O of this. So there is zijt minus z bar ijt. All right. And there is another one, because this is the case when I is equal to j. This should be ztii minus dt bar ii. Correct? So yes, this is correct. Yeah. Oh, no, this is j. I'm sorry, j. Here is it j? Yeah, this is j. Yeah, this is j. Okay, j, here we are. And then you have the backwards term, or the martingale term, I should say. And so this is ztij minus z bar ij t dbt. Okay, how to conclude? So here I forgot there is a big t dt. Okay. Well, for those of you who know backward equation, this is a stability argument. So what we want to say is that this 1 over n here is going to propagate to the difference of these terms and to the difference of this term. And this is exactly a stability argument or stability argument for backward stochastic differential equation. I forgot the J here, there is a J. So for BSDs. So you want to propagate 1 over n to the differences of the y's and of the z. In fact, we know very well how to do that if in the equation we have Lipschitz differences or linear differences of the same term. The small difficulty that you face in this analysis is that you have the square. This is a bit demanding, and in the first book with Cardaliaguet, Lasry and P.L, this was not really solved because we cheated. The Hamiltonian was Lipschitz, and you find the complete argument in the book with René. So here, to see how to handle the quadraticity, you can see Carmona de la Rue, volume 2, and this is chapter 6. This is, you have to pay an exponential, or you put an exponential to remove the square exactly as you do in Kohlhoff transformation, but you have to be a little bit more subtle. Except for this, this is quite standard, and then you completely propagate the 1 over n to the solution. And so what you have at the end of the day, so here I'm going to conclude, I think this is time for me to conclude. You have that supremum over the t's between yti and y bar ti is, let's say, squared 1/2 is c over n. And in C, you see the smoothness of the solution to the master equation. And for the Z, for those of you who do not know backward theory, once you have a term as the one in green, what you compute or what you can estimate is the energy of this term. So here the energy would be the sum over the j's of z t I j minus z bar I j t squared t is less than c over n squared. So I put a square here because there is a square. So maybe just to homogenize, let me remove the 1/2, and so you will get squared on both sides. So now once you have this, this is almost the conclusion of my story, and I think I will stop here. So what you do is you come back to this, equation. So this was the equation I had for the equilibrium. Right, so this is the equation for the equilibrium. Okay, let me remove the colors. And now let me explain to you what is the end of the proof. But now once you have this, this is absolutely standard. So this is ZTI with my notations. And so what you know from the previous line, so what you know from this is that this is minus z bar I t plus O of 1 over n. This is O in L2, but this is okay to have this in L2 and not in sup norm. So don't worry about this. Okay, dt. And so plus dBTI. And this guy now, this is exactly minus dxu txi 1 over n, the sum of delta xj, j from 1 to n. So this is almost a particle system. Now the very, very, very good thing, and this is this solves all the intuitions that we used or we have been using since Monday. This guy now, this is given. This is the solution to the master equation. So this is not an intuition. This is really something that exists. and makes sense from the mathematical point of view. And so this is a particle system. And what you say is that you propagate this 1 over n, and this particle system is a distance at most 1 over n from the same thing without the capital O. So you remove the big O, you take the same particle system, but without the capital O. And this one, this is a standard particle system for which converges to a Mach inverse of SDE. So here, this is a standard particle system. And we know that it converges. These are the results from Monday. It converges in some sense to the solution of the Mach inverse of equation d minus dxu, maybe I will put a bar t, the law of xt bar dt dbt. And we know, for instance, we can compare the distance between the empirical measure, or we can compare the distance between some coupling. Anyway, we have the rate of convergence for this. So at the end of the day, you start from, this is the equilibrium trajectory for the game. You know how far it is from this one. This is a distance 1 over n. And then you compare with this one. And once again, you know the distance. In fact, basically the distance, if you compute some Wasserstein distances, this is 1 over n to the power 1 over d. More or less, this is what you have. So this is the end of this proof, and I think this is a very good point to have done this argument, because it closes the loop, I should say. So you come back to the intuition that we had on Monday. So what I suggest is that we have a break, 5 minutes, and then after that there are two options. If you have many questions, we can discuss. This would be absolutely fine for me. Or if you want, I can just show you a few slides on potential games. I'm not going to write this down on the pad, just explaining to you on the slides. I think you had enough on the pad. So we can do that. So we can resume in 5 minutes if this is fine for you. And then either you discuss because you have plenty of questions, and then I stop here, I have said enough. Or if you don't have questions and if you prefer, I can show you some other things I had in mind to discuss, and I didn't have enough time for this, but on the slides only. Is it okay?
Thank you very much, François.
Okay.
Yeah, I think it is fine for everybody. Okay, so you take a break, and then either there are questions, we collect questions, written or voice questions, or you continue, show us some remarks and some slides regarding
exactly
potential gains.
Exactly.
Thank you. So we meet again in 5 minutes.
5 minutes. Very good. Thank you. Okay, so welcome back. So once again, I propose to do as I told you before the break. So if you have any questions, then I think this is a good time to discuss. Or if not, I can take let's say 15 minutes to explain to you, or maybe a bit more, but not too much, to explain to you potential games from the slides, so that you have a kind of complete overview of what I wanted to tell you.
Are there any questions by voice or written? No. Well, okay, I have indeed, yes, Mohammed. Mohammed Kibiri Alawi, you have a question.
Yeah, thank you. Just I have a question about the MFG system. Suppose we have two players, just two players, which will repeat the game many times. Can we adopt the principle of MFG to this type of problem? Instead of supposing that we have just two players with a repeated game, we suppose that we have a large number of players with the same game.
So you have many players, and they play the same game?
Yeah.
And so what do you want to get?
No. Just if you have just two players with a game, but the game is repeated many times. So a large number of repetition. Can we adopt the principle of MFG in this problem?
Okay, I don't see why you would like. See, if you have just two players, why do you say that? I don't see why. Because what do you expect? You expect that because of the repetitions, there is something that you could.
Because we have many repetition.
Yeah.
Okay, so like you have a large number of players who play.
But so each time you have a repetition, what happens after one repetition? Is there any update in the system, or?
Yeah. In every step, we have a strategy.
Yeah.
We have a game.
Yeah.
So we can get an equilibrium point.
But so when you restart the new game, what do you use from the previous one? There is an update in the choice of the strategy, or?
Yes.
Okay, so first I should see exactly.
I'm not a specialist, so my question can be with no sense. But
no, this is not what I'm saying. I was trying to understand exactly two things. The first one was when you repeat. Indeed, when you repeat, you have to say how you use the previous steps. So my answer is more than. I don't think that when you have just two players, you can really see the same type of things, because here really this is really these are really results for cases when you have averaging with respect to the population. So if you repeat things only with two players, I don't see, but maybe I'm missing something, which is absolutely possible. I don't see how you will get the similar averaging. Now, to answer your question, indeed, you could try to see what happens when you repeat, maybe not games, but some optimization problem in min-field games, and how you learn by repetition and equilibrium. So here, I think, from what I understand, but maybe I don't have a sufficiently good overview of your question to answer it as you want. But this would be my answer. If you repeat a learning problem in which you say, well, I just have one player who plays against the population, and the player updates or finds the best response given the state of the population, then at the next stage, the population is going to update itself, its own state. And then at the end of the day, by repeating this kind of updating and learning procedure, I should be able to learn an equilibrium. So this is my understanding of what we could think of. And indeed, these are things that exist. So there have been some papers on this learning strategy by repetition of the game, which is not exactly repeating the game. In fact, you have just one player playing against the population, or within a fixed population, I should say. And at the end of the period, you update the state of the population given the best response of the player. So this is a learning strategy that is called the fictitious playing game theory. And this has been applied to min-field games. From the theoretical point of view, there have been some papers by Kardaliage and one of his students, Hadi Kanlu. So I think there was a paper in 2017. And recently, several people have used this learning really in reinforcement learning. So they really put this in the machine, and they have some, once again, some reinforcement learning algorithm for minimizing or for finding the best response of the typical player in the population at any iteration. And then you update in this way. And under some assumption, at the end of the day, you see that the population is going to converge towards an equilibrium. So this would be my response. Now, for two players, it's not clear to me how you would see the emergence of the analog of a min-field limit, but maybe I'm missing something here. So this would be my answer.
Okay, thank you. Thank you. Can I?
Sure.
Okay. In the first of your lecture, maybe Monday or Tuesday, you speak about the uniqueness, and that the monotonicity ensure the uniqueness of the equilibrium. Okay, if we have not the monotonicity, is there an infinity of solution or something like that?
Infinitely, so there may be several solutions.
Excuse me. Why this question? Just to tell that if we have an infinity of solution, can we look about a class of solution where the uniqueness can be ensured?
Okay, this is a really interesting question. So the first thing is that we can have infinitely many solutions. So there are examples with infinitely many solutions, but there are also examples with just a finite number of solutions. Let's say 2, 3. So I can cook up examples and I can give you some references where you have 3, 4 solutions, or indeed, in some cases, you can have more. Now, your question is really interesting. So as soon as you lose uniqueness, indeed, this is a very interesting question to see whether you can select one of these solutions, or as you say, a subclass. And yes, there are some results, and these are some questions that I have been working on for several years. Let me try to organize maybe let me try to give you some references. So maybe this will be easier for all of you. So just to give you some references about learning, so to answer properly to your question. So the papers I was mentioning, this is the paper by Adikanlu and Cardaliague. So this is 17, and then if you find citations of this paper, you will see recent application with reinforcement learning. And so for selection, yes, this is a very, very nice question. So in fact, you don't have a general theory for this, because this is a very difficult question. So what you will find is a class of 1D example, because these are examples in which you can parameterize the equilibria by a 1D parameter. So equilibria are parameterized by a 1D parameter. So what does it mean, a 1D parameter? Let me give you two examples. For instance, there are examples in connection with linear quadratic stochastic control in which equilibria are known to be Gaussian. And so when the equilibria are Gaussian, they are parameterized by the mean and the variance. But in some model, in fact, you just have, or you have that the variance is fixed, because at the end of the day, when you compute the variance, it is given for free as an input of the model, and there is nothing to adjust when you look for the equilibrium. So now you just have the mean, and let's say that if the dynamics are one-dimensional, then the mean is going to be 1D. And so you can have a model in which the parameter of interest, so the main unknown, is in fact a 1D. It's going to depend on time, but the unknown will be a time involving 1D parameter. Another instance, these are mean field game on a finite state space. I didn't have time to discuss about this, but the philosophy is the same, except that the players can take at most a finite number of values. And then when the state space, the cardinal of the state space is equal to 2, once again, the mean of the population describes the state of the population. So the mean is 1D because the state is 2. So you just have to describe what is the proportion in state 1, what is the proportion in state 2. And this is a 1D parameter, or equivalently, the mean of the population describes the population itself. And so the mean is 1D. Now, why do I say this? Because when equilibria are parameterized by this 1D parameter, you can benefit, let's say, for instance, for the fact that on 1D there is a total order. And so you can more easily compare the dynamics. And this is easier to, this is certainly easier to select equilibria. So I can give you some references in this direction. So for the first one, I did a paper with one of my former PhD student, Fogen. So this was published maybe 19 or 20, I don't remember. And here there is, for the second one, there is a nice paper by Caines, Fischer, Daipra, and I think the last one is Pellino. And this is around the same date, the same year, 19. Another way to say that is to say that in this setting, and this is depending on your background, this might be really interesting. In this setting, you can have a look at the master equation, and the master equation becomes a one-dimensional, or I should say, a scalar conservation law. And this scalar conservation law, then you can use the results of the theory for entropy solution to characterize what should be the right solution to the master equation. It's not exactly the equilibrium itself, but this is very connected. So somehow, at the same time, you can also select a solution to the master equation because you benefit of the theory of entropy solution for scalar conservation laws. Okay, so this is in 1D. Now in higher dimension, there are very, very few things. And in fact, to the best of my knowledge, there is just one paper that I just did with Alekos check-in. So this is in review, where we addressed games with finite states of any cardinality. So this is a generalization of the 1D of the two element case, because now you can have as many states as you want, provided that the number of states is finite. And plus, there is something that I have not spoken about. There is a potential structure. So potential means that, very easily to explain to you, let's say that the master equation is going to be the derivative, so it's going to be the gradient of some HJB equation. So this is exactly what happens in potential game for the math point of view. When you have this master equation, this is not a HJB equation, but in some cases, this is the derivative of a HJB equation. And then in that case, you can give some selection principle. And our result with Alekos is to say that the equilibria that you select should be the minimizers of the problem which is behind the HJB equation. So in the HJB equation, you have an optimization problem or an optimal control problem. And in fact, you have a class of minimizers for this one. In fact, many of the time, there is a unique minimizer. There is a theory for this. And so what we say with Alekos is that the selection should say, or should give you, or should tell you to reduce the possible equilibria to the set of these minimizers. And to the best of my knowledge, there are no other results. So this is a very nice question, but this is also very challenging because the master equation is this is a hyperbolic system. And so we know that I'm not a specialist of this question, but from what I understand, this is a very difficult question to see what should be the selection for hyperbolic system. And so this is expected to be very challenging. So we must move step by step. First, 1D parameter model, and then a potential case, and maybe tomorrow there will be another model. But I don't think we can expect directly. Maybe I'm too pessimistic, but it seems that we should proceed step by step to have some classes of examples for which you can do a selection.
Okay, thank you very much for your
Thank you.
Answer.
Thank you.
Are there any questions? Other questions? If not, maybe Francois, I reduce my questions to one, and then we take time to
discuss
the remaining discussion later. Okay. I just would like to ask you if we take the crowd dynamics example you were introducing in the first lecture, and we want to model the crowd dynamics with MFG. Mm-hmm. Is there a simple way to model the fact that maybe the population is the state of the crowd depends on the whole distribution of the whole crowd, while maybe in many situations the perception they have is only local perception. I have a local perception of the crowd around me, but of course my state depends on the whole crowd.
Yeah, absolutely.
Thank you.
So this is a very nice question. So thank you. So in fact, this is something I have not said. When you have the mean field interaction, what I said indeed was that. So I put in the mean field model. I put cost of this shape, so F, mu, and X, and I told you mu is the state of the population. Now, what could be absolutely possible is to, at least formally, and then I will explain, is to say this running cost is going to be, so it depends on X and mu, and what I could do is to say it will be a function of X, and I'm going to compute the local density of my population at point X. So really, this is the local density, or the density at point X, in fact. And this is absolutely consistent with my formulation. Formally, if I am given mu and I'm given X, provided that there is a density for the population, it makes sense to say that the cost of X and the local density is a function of X and the measure. And I think that in your mind, certainly this is what you think. So I see just the local density of people that are around me. And indeed, this is what people use in crowd models. So there are plenty of many people using studying crowd models within MFGs. And most of the time, indeed, these are people from the PDE community, because for them, this is really natural to use the density as a mean field interaction. Whilst from the probabilistic point of view, this is a little bit less common for the simple reason that if you come back to the particle system, the notion of local density is not well defined. And so you have to make some modification of the local density to give a meaning to the particle system. So certainly, I think that Diogo Gomez did some papers. I'm sure that Yves Ajdou has some papers on this with some numerical simulation. And I think that Filippo Sant'Ambrogio also did some papers. So you will have some models really with mean field games. Yes, exactly. So I think that these are good references. Now, the main mathematical difficulty with this formulation regarding all the things that I have told you is that if I choose this kind of interaction here, for sure, this is not smooth with respect to the Wasserstein distance and with respect to all the, or this does not satisfy all the requirements that I put before on the type of topology I had on the space of measures, because when I have a look at the local density, this is something that is that requires another topology than the one I use. So it's going to require certainly another formulation of the assumption, but once again, you will have PDE systems. So for sure, you will have MFG system with this model, and in the Fokker-Planck equation, so you will get the same equation, but in the HJB equation, it will become a local interaction. So you will see the local density of the population. So there are plenty of papers in this direction. And for the master equation, if I remember well, I think that Pierre Cardaliaguet did one paper where he explained how to adapt the arguments that we used in the book to the case with a local density. So I'm pretty sure that there are some results. But once again, formally, it's possible. This is the same framework, but you have to pay really attention to the way you do the maths, because conceptually the tools are a bit different. So the kind of yes, the setting is not exactly the same. So you have to be careful in the mathematical analysis. I don't know whether this is the answer you expected or not.
Yes, thank you, Francois. Thank you for the references. And
okay. If you want to discuss more.
Yeah, thank you. I'll take, okay, it's okay for me.
Maybe also Daniela Tonon, maybe did also. Daniela Tonon, maybe could be another name. Yeah. Sorry. Yeah.
Okay. Thank you. If there are no more questions, please, Francois, proceed to the last slide.
Yeah, okay. Okay. Yes. I can speak about this if you want. So let me find this. Yeah. So yeah, this is something that I have not spoken about, and so I think this could be interesting for you to have a look at this. Let me explain to you the practical motivation if you want to compare with what you can find in min-field games. The first thing is that in addition to min-field game, you have another expanding theory using the same tools, but the modeling is a bit different. This is what we called min-field control problem, or min-field control theory. And it corresponds to the case when the players, instead of being selfish or instead of being in competition, now they do cooperate. So there is a cooperation between the player. And so if you take the same example as the one we had before, so let's say that the dynamics of one given player is this one. Now you say that everybody has the same cost as before, but now what you want to minimize is not, this is not JI for any given player. No, what you want to minimize is the total cost to the population. So what you want to minimize is one over n, the sum of the cost. So conceptually, and this is what he said in the slide, another way to think about this, at the end of the day, this is the same problem, is to say that if you reduce yourself to Markov policies, as we did before, then there is a kind of chief, which is called a central planner, that says to the players which feedback function they have to use. And so, well, this formulation is a bit, this is not exactly correct what I put in this slide. I should correct, by the way. I'm saying that, in fact, what the central planner is going to say is all the players are going to choose this for the same function alpha, depending on their own state and the global state of the population. So I am the chief, and I'm telling you which strategy you have to follow. And all of you, because you work for my company, for instance, are going to play the same strategy, but now they implement this strategy at their own state, and also depending on the state of the population. And what the central planner wants to do is to minimize the global cost to the population by tuning the shape of alpha. So this is the same idea that players are going to cooperate in order to minimize the global cost to the society. And so now, exactly as what we did for min-field games, the question is how to derive an asymptotic formulation for this. So we would like to let the number of players tend to infinity and to say what is the problem that you eventually minimize when n is equal to, or the problem that you eventually solve when n is equal to infinity. And so the formulation is pretty much the same, but the difference occurs. It occurs in the place where you put the limit. Somehow in min-field games, somehow you pass to the limit and then you make the optimization for one agent. In min-field control, you optimize and then you pass to the limit somehow. So there is a kind of order on the fashion you pass to the limit. So what you say is that in min-field control, since everybody uses the same feedback function, in fact, when you change the value of alpha, you change the whole state of the population. So this is not as in min-field games. In min-field games, when one player deviates, you don't change the state of the population. In min-field control, since everybody uses the same feedback, if the chief says, well, let us change our policy, everybody is going to change. And so the global effect or the global impact on the population is really clear. And so you have to change the state of the population. So the formalism that you have at the end of the day, this is that you take one typical player in the population. So let's say that this is one small company working for the big company, for instance. And so all the small companies behave statistically in a similar manner. So here, this is the same dynamics as the one that we had for the typical player in min-field games. So you recover the same, except that in my slide, the model is a bit more complicated. But now I'm saying that instead of freezing the environment as I did before, so before this was the environment and this was frozen before the optimization, now I really put the law of xt. So you see that the law really depends. So this depends on the choice of alpha. Because when alpha changes, the law of the population is going to change, or the law of xt is going to change. And now what I want to do in min-field control is precisely to optimize this cost functional with respect to alpha. So this is optimizing the state of the population with respect to alpha. So this is really a control problem, but the state variable is the state of the population. So this is a measure. And for those of you who know optimal transportation, somehow optimal transportation is an example of a min-field control problem. It is a singular example in which, in fact, I say the first thing is that in optimal control, there is no noise. If you put a noise, this is entropic optimal transportation. So if there is no noise, this is just alpha. And so what you want to do in optimal control is that you want to choose the best possible alpha for the kinetic energy so that the state of the population at the end of time is exactly at a given target. So you pay infinity, or you pay an infinite cost if you don't reach the target. And otherwise, if you reach the target, you just pay the kinetic energy that has been used, so the integral of the square of alpha that has been used to reach the target. And so this formulation of optimal transportation as a mean field control problem comes from the Benamou-Brenier theorem on optimal transportation. I don't think that Benamou-Brenier wrote this exactly as a mean field control, but if you have a look at the statement, this is exactly what I told you. So at the end of the day, you can rephrase the statement by Benamou and Brenier as a mean field control. Another way to recast things beyond the single scope of optimal transportation is you can rephrase the dynamics that you have here. So these dynamics, by saying that alpha, you play alpha as a feedback function. And so you say, well, instead of having a look at the evolution of one typical player in the population, I have a look at the dynamics of the population. So this is this one, which is a Fokker-Planck equation. And so what I want to do is to optimize my cost functional, so the same as before, over a Fokker-Planck equation. So this is exactly the reformulation here of the cost functional, but now the state variable is the solution of this Fokker-Planck equation that is obtained by computing the marginal law of my reference player. And so the formulation, the way you pass from here to here, this is just using the fact that mu t, the mu t that you have here has to be the law of xt. And so you rephrase the expectation as an integral over mu t and the same for the running cost. And so somehow you can regard mean field control as a deterministic stochastic control problem, but in infinite dimension, and the state variable lives in the simplex. So the example that I have been discussing so far, this is B alpha is equal to alpha. So this is the same example as before. You just tune the velocity of the particle, think of optimal transportation. And here, this is the same example as the one I had before, but this is a cost. This is the same type of cost as the one I had. And so I say that if you prefer, let me write this properly. So let me erase these green colors. So here, when I take this formulation, and if I choose precisely this as a functional, so this is the shape of G, I would have 1/2, so the integral of gx minus y d mu ty d mu tx. So you see that this is really a typical example for an energy, an internal energy of interaction between the particles in the population. So it doesn't depend on x. This is the global cost that I obtain for the population here when I'm using this G as an example. So this is a typical example that you can find in the literature on the shape of small g. And so this is given as a convolution kernel. And at the end of the day, it says that there is a global energy for the population, maybe global potential energy for the population at terminal time, and the same for the running cost. Okay. So now you have an infinite dimensional optimal control problem, and certainly, if you know, maybe here I should explain specifically for those of you who are not so aware of control, but when you have a control problem, you compute what we call the Hamiltonian. So the way you get the Hamiltonian is to make you let your state dynamics. So here, this is the state dynamics that you have. So this is the state dynamics. Act onto, so the state dynamics is here. And you let this act on a dual variable that is going to be in the end associated with the, let's say, with your optimal strategy, let's say. So here, the variable, the state variable is a measure. And so the dual variable should be intuitively in the dual space. So this should be a continuous function, let's say. And so the way you get the Hamiltonian is in this way. So you let act your dual variable that is a function u on the dynamics of the Fokker-Planck equation. And so by integration by parts, you get these two terms. So you see that this is just a mere integration by parts from the Fokker-Planck equation. And so you have that the dual variable u, after integration by parts, I need integration by parts in the Fokker-Planck equation, really in this equation here. So I multiply this equation by u and I integrate by parts after integration with respect to mu. And so I get this first term in the Hamiltonian, and the second term in the Hamiltonian is the cost. So this is the usual Hamiltonian in the control theory, except that now this is infinite dimensional. And then what you have to do is to compute the optimal feedback in terms of the dual variable. So the dual variable here is u, and in order to compute the optimal feedback, you have to minimize exactly this quantity. And so you realize when you pass everything under the same expectation that basically the optimal feedback will be given by minus the gradient of the dual variable. Okay? And now there is the Pontryagin principle in control theory. This is not the stochastic here because there is no stochasticity. My problem is completely deterministic. This is just an infinite dimension that gives you what is the dynamics or what should be the dynamics of the dual variable to compute at the end of the day the optimal feedback according to the rule that I gave you here. And so I'm going to duplicate in yellow. So you say, I'm sorry, this should be in yellow. So you say u is going to be or will be understood as the dual variable, and the dynamics of this dual variable is exactly given by the Pontryagin principle. And so you have the Pontryagin principle here. And now the way you get the Pontryagin principle is to take the derivative, to get the derivative of the Hamiltonian with respect to the state variable. So in fact, what you must do to get this, you must compute the derivative, there is a minus in fact, with respect to the measure mu. And here this is a standard linearization. So this is, you can do that by using this extrinsic notion of derivative that I used yesterday, or I explained to you yesterday. And you get exactly this equation in yellow as an equation for your dual variable, okay? And then at the end of the day, when you plug this rule in the Fokker-Planck equation, because keep in mind that the Fokker-Planck equation was the equation for the population. So when you replace alpha here by minus the gradients of the equation that is in yellow in the bottom of the slide, you get a forward-backward system. So you get an HJB equation for the dual variable, and for the state of the population, you get a Fokker-Planck equation. And then you realize that the Pontryagin principle gives you a necessary condition that must be satisfied by your minimizer. So this is not a sufficient condition, except if you have convexity. This is a necessary condition. So it gives you the critical points of the cost functional. And so when you apply Pontryagin in mean-field control, what you realize is that the critical points are described by a forward-backward system, Fokker-Planck HJB. And so the conclusion of this story is that the critical points of a mean-field control problem are the solution of a mean-field game. And this is the reason why, beyond the tools themselves, so in fact, the two theories share many, many common tools. If you want to write down the HJB equation for your mean-field control, you have to play with Wasserstein derivatives, as I did yesterday. So there are many, many similarities in the tools, but even more, they are really connected in the sense that the critical points of my optimal mean-field optimal control problem here, my critical points are the equilibria of some mean-field game, and the mean-field game here is exactly the one that is described at the bottom of the slide. And so this is, you have your typical player as we had yesterday, and this is the cost to your typical player in the MFG, in the related MFG. So this is the main thing that I wanted to tell you. So once again, mean-field games are first-order conditions of mean-field control. In fact, I should be careful because I'm not claiming that any mean-field game is a first-order condition. I said the converse. Typically, if you start from a mean-field control and you take the critical points, basically this will be a kind of mean-field games. And so at the end of the day, it tells you that the costs are not the same. The cost of the original mean-field control problem, I insist on this. So the cost that you have here, this is driven, let me tell you where this is. This was really driven by, here this was the double integral. Unfortunately, I erased this. So this was the double integral, for instance, for the terminal cost over the whole population. So this was the cost for the mean-field control. We put a C for control. Whilst if you have the cost for the MFG, it is in this example, there is just one simple integral. And even though you integrate with respect to the law of the equilibrium, what you get is that this is G of x minus y mu ty d mu tx without the 1/2. There are some differences. These are not the same cost problem. So these are not the same cost. And it says that the costs are not the same, but the solutions are the same. And this is really interesting in practice. There is a philosophical application of this because it says that, well, in practice, people are selfish. So you know that, except if they have really to obey the chief, but if not, like people in a roundabout or in the crowd, in a big crowd, people are selfish, and certainly they will behave as a Nash, as a mean-field game. But now, if you design the whole of the airport or whatever, if you design any system that the players, the agents, the individuals in real life are going to use, when you design the system, whatever the system is, somehow you are the chief. And you should design the system in such a way that people, when they are selfish, behave in a given way. So you say, I am going to design a mean field control problem. And this is what I would like people do if they were obeying the chief. But I know that people are going to be selfish. So I'm going to formulate the system in another way with other kind of costs, keeping in mind that people are going to compete, so that at the end of the day, the equilibrium that is solved by the Nash is exactly the minimizer of the mean field control. And this is what we call in practice mechanism design. So this is a way to force somehow people to do things. So there have been a series of papers a few years ago. I think that in particular, René Carmona did several papers about this and what is called the price of anarchy. So this is what you have to pay when people don't obey the chief. You have to pay an additional cost, and this additional cost is computed through the price of anarchy. So René did several papers in this direction. This is just to tell you from the practical point of view. So there could be an interest for this connection between two problems who seemingly look different, but in fact, conceptually, they share some connections. And from the math point of view, this is what I was telling as an answer to the questions that I had. When a game is, so I forgot to say, a game is called potential precisely when this derives in this way from a mean field control problem. So a potential game is a game for which the MFG system is precisely the Pontryagin system of a mean field control. So as I told you, we cannot say that all the games are potential, but when they are potential, then we know that it's really meaningful to have a look at the minimizers of the mean field control. And this is what I was telling you. We expect that the right equilibria in that case are indeed the minimizers of the mean field control that is above. There might be equilibria which are not minimizers of the mean field control that is above, but it makes sense to say that a correct selection principle should be that one, and then you have to prove this selection principle by some arguments. Okay, so this was just things that I wanted to say. I think that this is really important for you to know the existence of this connected theory, optimization under the planification by a chief. The problems look different, but at the end of the day, at least for mean field games which are potential, there are some obvious connection between the two, as the Pontryagin system is precisely a mean field game system. Okay, I think this is a very good point for me to stop. So thank you for this 4 days. So what we have to do with Abdou now is to maybe to put the slides and the lectures easily in a manner that is easily available to all of you.
Yes. First of all, Francois, let me thank you in the name of the all audiences for the 4 days.
Thank you.
In the name of the institutions that collaborated for these lectures to happen. Thank you so much for this very exciting and very they were captivating for us to follow the proofs and follow the presentation. Thank you very much.
Thank you, Abdou. Thank you so much.
Please, I have sent a link. I will send it again for a Google Drive link to get all the material that was sent to us by Francois. So you will have the present lecture, the presentation of today, the notes of today will be there.
Absolutely.
Okay. So thank you very much again, and I hope that we will meet very soon for.
So who is the next speaker?
Yes, thank you. So I almost forgot that this is the last lecture of this.
Okay.
This is last open doctoral lecture for this year, and on September we will have in lectures dedicated to optimal control and applications, and will be given by Lahsan Manyar from University Qada'iyat.
Ah, very good, very good. Okay, so looking forward to seeing you in the next lecture. Okay, so I will send you the document. Thank you. Okay.